So a few announcements. The problem of the month is for $25 due on Sunday night. That's $25 if you give the best solution. So, and we are planning on having a bowling event at the Union next Saturday. That's October 6th. And we would like to have RSVPs for that, so we're going to host an event on Facebook for that. So if you're not already on Facebook, you can just search UT Math Club and you'll find it on there. And that's what I got. So our speaker today is Dr. Bussin, talking about making tracks mathematicians play with trains.
Thank you. So you have to understand how this happens. You try to be like a normal person, right? And I don't know, you do things like play with your nieces and nephews and things like that, and the toys come out. And you just play like you're supposed to play, but after a while you start thinking, you know, there's some math in here. And then it gets you, and then like the kid is off playing and you're off thinking, and then you're a lot of notes on scrap paper and stuff like that. So I was playing with one of the nephews, and we were playing with the wooden train tracks. So you've seen these things. They're actually pretty well constructed. They've got a little space that you can insert a little knob into. Oops, so it's got a space on one end and a little knob on the other end. And they've got grooves for the tracks on here. And the little Thomas the Tank Engine can, you know, go along the train tracks. And your job then is to link these together to make a cool little track so that your friend can make the trains go. Well, so I did what everyone else does. You take the train pieces, and the first thing you do is you just make a little circle, and you think, oh, this fits nicely. It fits into a nice circle. But then you start to think, well, you know, I wonder what other shapes we can make. And you could do anything you want. There's no rules for this game, right? You just do whatever you want. Most people like to have train tracks that form a closed loop, so the train doesn't go, you know, off the cliff. So you want the piece to somehow kind of come back to where you start. And that's it. You'd like to be able to put the train track pieces together in such a way that you're not breaking off the little things, because they do break off. And in order to make that work, you want to get the pieces lined up so there's not a lot of torque on the little knobs at the end. And they're designed to fit perfectly as long as you've got them kind of at the right spacing and the right direction. So I wanted to come in and like, you know, have a lot of train tracks to show you, but it turns out that these things are really expensive to buy. I didn't want to buy it just for this talk. But I did bring in some paper equivalents of train tracks. And you'll see that they actually come in two different shapes. There's curvy ones and straight ones. So I thought, rather than just have me tell you all kinds of answers, why don't I get you guys to play for a little while? So I put the two tables together over here. There's another little table over there, and there's some floor space over here. And I got, oh, I don't know, about 50 or 80 of these curved ones and a few dozen straight ones. And you have to pretend that there's the little knobs on there, because I only wanted to spend so much time cutting pieces of paper out this afternoon. But you want to do it? You want to just come up and let's just spend maybe, I don't know, 4 minutes or so just trying to come up with some cool shapes. Now, you can probably already guess some shapes you can make, but, you know, let's just see what you can come up with. Yeah, start one over there, and you can start one over here, because I don't know what you can do. And these shapes tend to get kind of large, so you need the whole living room sometimes.
So many pieces.
Oh, I mean, I can maybe borrow some from the other table if we need.
Can they cross? Are they able to?
It's up to you. It's up to you. Yeah, actually, the poster for this talk, I took a picture that had a little bridge in it. So.
just aren't there. Isn't there some sort of thing? Isn't there like close? What if we do a space here on the counter along the?
What does that mean? What does that say about me?
It's like last minute you curve off or I don't know.
Oh, is that the bridge?
Yeah.
That's some pretty sweet bridging.
Thank you. Well, it was. Three of them. Because you came in late and thought they were bridging.
Oh, where are you going? I'm pretty sure it's the coolest one.
Oh, also, looks like a
So how about we try to make
We made some like really ugly trefoil.
the trefoil not it's like a Mobius strip that way and then
but maybe a straight one.
yeah, that'll work. I was just gonna grab one of those.
Yeah.
Yeah,
Let's go ahead and make it one. Let's connect wait, go that way.
What?
This is like a strip. So we want to go over on this side, right? No, if you flip, if you have a piece that twists here,
yeah.
if you have a piece anywhere that twists. Oh, okay, doesn't have to twist. We don't have it. We want to make it twist. No, but if this one make it twist.
No, you make it twist. Let's do it.
Think about the curve that you can't change.
Connect this one to this one, and this one go over because here you guys. What does one wants to go? This one wants to go over.
And then I feel like I'm at an NBA game. There's like kids on the court.
And then just connect it, right?
Yeah. But it's not gonna roll. I made my
That is cool.
Alright, Brewmeister moves. Undo it. Brewmeister
Oh, it's so cool.
undo that knot.
It's
undone. Go check back on team number 2.
Yeah, I got a little one too.
What is this?
It's going big. It's not. I will murder an R.
Yeah, they were doing some under and over.
All right.
All right, well, I said I'd give you 4 minutes. You want more time to do that, or what do you want to do?
I think it looks like a. Where's the map, yo?
Yeah, where's the myth? Well, I don't know. I heard some cool math being mentioned. Somebody said something, I heard the word Möbius, and I'm suddenly thinking, wow, I never thought to do that, to have the train track, have the train come up on the back of the underside of the train tracks.
You have to pretend the table's not there, but it works.
We're good at pretending.
Well, they may.
Floating in space.
You've seen I can have a physical Möbius strip, and it sort of like stands up, and so the train just has to kind of go sideways for a while.
It needs to be like a rigid body and then the tracks. The rails can connect to go all the way.
This is the raddest one.
All right, let's leave these here. Did you guys get one or more closed curves?
I know.
Okay.
We were all like really impressed with ourselves.
Well, then leave them. We'll make them work.
It's like trick.
All right, that was great. That was great. I mean, I heard somebody say trefoil. I hadn't thought about doing that. The trefoil knot is a famous kind of knot that it's easy to sort of show a picture of it, and you can make it out of train tracks. Now, so what questions did we come up with as you were playing? I mean, what occurs to you? You're the mathematicians now. You have to come up with your own problems in addition to solving problems. You have to invent problems. That sounds kind of negative. Anyway, what mathematical kinds of questions, or what think of.
Like with a given number of pieces, how many times can you loop around any one point?
With a given number of pieces, how many times can you loop around one point? So actually, if you take the complex variables course, you know about the winding number. So I guess you're asking how much winding can you do around a given point? And of course, the more pieces you have, the more you can go. I suppose if you had sufficient support, you can make a sort of a spiral, right? You've seen like train tracks often come with little spirals, so things can go up and down. That's true. Good. Somebody over here was asking about crossing. So now we have questions too about whether or not. Well, I think there's crossing issues on this one as well. The questions as to whether or not the shapes that we're envisioning, sort of as seen from the bird's eye view, can we build them in three-dimensional space, you know, with the things that they give to us? So that's another question that shows up. More.
Combinatorially, given a certain number of pieces, how many closed tracks can we make?
Yeah, well, so with given sets of equipment, what can you actually make? So, you know, for instance, over here, I guess you guys must have had just a few curved pieces left over, and the three of them, like, yeah, I don't know if you can see all these things, but so it looks like do I really have to wear this thing? It looks like the hazardous, that symbol for biohazards or whatever like that. So it looks like this. There's a curve, and then another curve, and then another curve. And the pieces touch, so it's a good train track, right? No? Why not? Yeah, you need some sort of smoothness in here. Now, so topologically we understand, or, you know, in differential calculus we understand the concept of a smooth curve. And you need that on real train tracks because the train has to go smoothly from one piece to the next. And physically you wouldn't be able to link things using the little knobs because you put too much twist in there. Okay, now the question is that sort of suggests the question of whether or not these other ones that we make that look good, how do we know that they're really right? You know, or did you kind of like twist just a little bit, you know, just to kind of make the pieces fit? Was there more torque on there than the train tracks would really sustain? Or even if the train tracks would hold together without falling, you think, well, yeah, but it's not elegant if it doesn't like match perfectly, right? So we do have the question of, well, you know, what can you make? And that's going to depend in part on the starting values, on the starting pieces that you have. And then we have the question of, well, how do you assess whether or not you've got something that's for real or just an approximation? And then you have the questions of, you know, can you enumerate lots of possibilities? All right, so lots of things that you can come up with. All right, so let me tell you what, in fact, how these pieces were made. They were supposed to come in only two congruence classes of shapes. One of them is essentially a straight line segment, so it's this narrow rectangle, the width of the track. And if this length is called that 1 unit, then these other sections are exactly 1/8 of a circle whose radius is 1. So those are the pieces that I gave you, and so there's some sort of mathematical cohesion between the two types of shapes. All right, so with that in mind, you can sort of describe to someone what are the shapes that you made. So if you took this home and you started to play around and you wanted to tell your friend, oh, I got this really cool shape, how would you describe it? How, like in words, so you can do it over the phone. How are you going to tell your friend what this shape is? How can we transmit this kind of information? So in other words, for those of you who are like computer science people, the question is, what kind of data type can I set up to describe the objects that I'm studying? Any suggestions? What are you going to?
Send like a sequence of, I mean, if you only have that one round shape and one straight shape, then I guess you have like 3 possibilities. It's going left, going right.
So 2 objects became 3, right? Because the curved pieces can be turned upside down, and physically they're made that way. There's little grooves for the train wheels on each side of the piece of wood. So the curved one can be turned so that as you're looking at it, as you move in the intended direction, I guess, is this the intended direction of motion? Is it curving off to the left or to the right? You just flip it over. Or then you could have the other piece which goes straight. And then what were you going to say with the sequence?
Oh, I was just saying if you're trying to, I guess, you know, tell your friends what it looks like. If you say, you know, okay, piece 1, piece 3, piece 2, you know, and that's how you would, I guess, build it up. And
sorry, so
because they're linked together in some sort of sequence, they have a relationship to their neighbors, I guess.
Right. So now, you guys on this table, you were making something else where there was a certain amount of branching in the train tracks. Okay, I guess they sell train tracks that have little branching things. I didn't allow for that possibility when I was getting ready for today. So well, I was just thinking that the train tracks were one-dimensional, topological, continuous. So there's just sort of a path, a single path that you're traveling, in which case we can just describe the whole curve by just giving the path. How do I know where to start? You have to start somewhere. Yeah, it's not going to matter really, right? I mean, because the whole point is to have a closed curve. So I can take any starting position and then just tell the sequence of things that I see until I get back to where I started. So here I've got this starting at this point. Oh, and how do I know which direction is the forward direction? Again, it doesn't really matter, right? But you have to pick one. So I would describe the curve by saying starting, let's say here, and going in, let's say, that direction. I have a left turn, a left turn, a left turn, a right turn, right, a straight. That doesn't look like a real good angle in there. I'll see if I can horse it around a little bit. And then a left turn, and a left turn, and a left turn, and okay. So you've got the pattern of what we're doing. So we can actually identify the mathematical objects that we're studying. It's going to be a sequence of a sequence drawn from taking some repetition of elements of the set that consists of either, let's go straight or left or right. And you have n of them. So the exponential notation means that it's a Cartesian product of lots of these sets. So a sequence is just an element of the set of all such sequences. So you just say straight, left, left, right, left, straight, whatever. Or if you like, there's nothing special about as far as enumerating these things, there's nothing special about the letters that I've used. You can just think of assigning these some kind of 3 different symbols, and that's all you need to specify the train track. Now, you wanted to talk about, what are the different possible shapes that we can make. You're going to notice pretty quickly that some sequences that you write down will actually give you the same shape because, well, like I said, you can start anywhere when you're describing the shape. And you can go in either of 2 directions when you're trying to describe the shape. So we might say something like 2 tracks are congruent if, if the sequence of zeros and ones and minus ones or S's and L's and R's really describe the same shape. And I think I can describe actually 3 different ways in which you could get 2 tracks, 2 such sequences that describe what I would call the same object. One is that you could be describing the same sequence but starting in a different place. So I could say that this shape is congruent to any a sub I, comma, a sub I plus 1, comma, dot, 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 up through an, followed by a1, and going up to a sub I minus 1. Right, so it's a formal way of describing the fact that if you start someplace different, you haven't really changed the shape of the track. The other thing that you can do is to say that 2 shapes will be congruent if you start in the same place, but you go in different directions. So if one of them is a1 up through an, where each one of these a's is one of these 3 symbols, what's going to be, what would be the sequence that you would get if you went in the opposite direction? This? Is that what you mean, negatives? Well, I'll leave this for a second here. But what is the result of replacing each? I assume that you're thinking of this instead of, I don't know what negative L means. But if you change the signs of each of these things, if 0 means go straight, 1 means go left, and minus 1 means go right, if you change all the signs, what does that do? Here, if I go left, 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 right, straight, left, 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 etc. Oh. What's this? Okay, twisty, we got an extra little motion in there. So if I change it, so instead of going left, left, if I go right, 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 left, straight, etc., what am I going to get?
Like a track flipped over?
Yeah, it'll be like flipping the track over, or it'll be the mirror image of the track. Okay, and I think I would accept that as a notion of congruence. So 2 shapes will be called congruent if you can get from one to the other one by shifting the signs. Just change the signs uniformly throughout. But that doesn't change the direction along which we travel. What would be the sequence that you get if you wanted to travel over the tracks in the opposite order? Yeah, AN, comma, AN minus 1, comma, etc., go down to A1. So just like in permutations in the symmetric group, right? If the inverse of a permutation is the same things written in the opposite order, and for basically the same reason, well, I should just say that these two things, you can consider those to be congruent. Okay, now actually I think, let's see, if you have a piece of track and you are originally going left, then if you want to do things in the reverse order, when you come around to this, that same piece of track will now be going to the right. So if you really do just what I said, you replace this one with this one, that will give you the mirror image track traversed backwards. But that's okay, because what I want to say is congruence will be the smallest equivalence relation that uses all three of these things. So any two tracks will be considered congruent if you can get from one to the other one by doing a succession of these kinds of operations. Okay? So if you wanted to start doing things on a computer and you want to say, well, I'm getting too many duplicates, I would like to consider two tracks to be congruent, and therefore I don't want to list them twice if I can get from one to the other one by any of these three kinds of maneuvers. And so what you might want to do is, as you do your bookkeeping, just consider all possible sequences and say something like, when I wrote my little computer programs, I said, out of all the possible ways that you could represent a track, so a congruent set of symbols, use the one that comes lexicographically first. And that way you won't get any duplication. Great. So, so we start to get a sense of what kinds of tracks you can make, and a way of recording them, and a sense of how to avoid some duplication. Now, for my next trick, let's try to think about some closed curves that you can get. Oh, so maybe I should write these down before I yank the pieces of paper away, because I want to do some demonstrations that you guys won't be able to see too well. Can someone, since you're closest, can you read me using that language? Can we record this one shape? Because one of the things I want to do at some point is to decide whether this one is for real. So let's write it down so I don't lose it. So where would you like to start? Okay, and which direction are you going to go first? Okay, so can you double check him as he yells it out? So what have we got here?
So right, left, right, straight, two lefts, five rights, two lefts, two rights, three lefts, three rights. Two rights.
At the end it's just two rights?
We start from here.
Yeah. Oh, okay.
So that looks like if you had one, so you have a grand total of 4 right turns together in the middle there somewhere? I see 1, 2, it looks like 5 actually.
The last one should be 3 then.
It should be 3 after all. Okay. So if we did it right, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 17, 19, 21, 24, 27 pieces of paper. Oh, I can't count that high. Okay. So yeah, we can look for notation that'll shorten it. And so I'm starting to use like a group theorist's notation, right? LLL is L cubed. Great. So I will look at that one later, and I'll give you some mechanisms to decide whether or not these things are for real or whether they're just kind of an approximation. Now, by the way, approximations are fine. In real life, you try to do things, and you know, if you have, I mean, this here I've got everything kind of elegant, right? It's exactly an eighth of a circle, and the radius of the circle is exactly the same as the length of the straight. But in real life, if you had kind of random pieces and you had to fit them together, you sort of do your best. And things might not be perfect, but then you might come up with some measurements of just how far from being perfect you are. Like, you know, how much are you forcing the pieces together? And then you might accept things that are within a certain tolerance of what we would consider to be absolutely correct. But I'm not going to do that. I'm not going to use that approach in this talk, because you'll see that I get some cool number theory if I insist that things work out exactly right. Okay, good. So now I can rip this thing apart, yeah? So if I asked you to come up with cool shapes, closed curves. If I didn't go for cool and I wanted simple, what could you do?
Circle.
Circle. Okay, so I said that these were eighths of a circle. So indeed, if you take exactly 8 of them, that should line up to be a full circle. And that is, in fact, the simplest closed curve that you can make with these pieces. Now, I don't know what, well, simple. I'm measuring simplicity by the total number of pieces involved, I guess. What would you say is the next simplest? Yeah, I think I heard somebody say ellipse. You won't get an ellipse, of course, because there's no, an ellipse cannot be made out of circular arcs and straight arcs. But you do get what I guess most people would call an oval or something, and you insert a couple of straight edges right in here. Okay, so now you've had the circle, and you've also got this. So this is a circular, that's a semicircle, this is a semicircle, and then you've got these straight arcs. And at that point, you realize that, you can generalize whenever possible. This is the math building here. Generalize whenever possible. What can you say? What did we just do that you can keep doing? You can add straight segments. Well, can I put them here? So I tried to put I just moved a couple. I mean, I took the circle, I split it, but not exactly in half. I took a 3 on the top and 5 on the bottom, and then I tried to put in the straights. Oops. And guess what? It didn't work.
It has to be a group of 2 or 4 curved segments. Or every other.
Yeah. Okay, so here's actually the procedure that will allow you to insert a pair of straights. What you need to have is, there needs to be, I really don't care if it's, you said 2 or 4 curves. I don't actually care what happens when you take see, here I had the circle and I split it and I inserted 2 straights. But I can have, some kind of fancy curve going on. Obviously this is taken from far away because you'd have to make this out of lots and lots of little curvy pieces. But if my curve used to go on like this, and if I decide to split it right here, I can do that and insert a little straight piece right in there. But what would I have to do? You have to add another one. Here? Here?
It has to be symmetric.
Well, there's not a whole lot of symmetry to this curve. And actually when I pointed over, I don't know where I pointed the first time. Actually it looks like I could insert it here, I bet. Let's close this guy. Seems to me that there's a spot right around here that I could snip. Yeah, it's the direction, right? The bearing or the heading of the train track at each point of each of those 2 points that needs to be the same. So if you ever have a closed loop where there are 2 points anywhere on the curve where the 2 tangent lines are parallel, as long as you're heading let's see, is it? I guess I was going to. I think maybe I was going to put some conditions. Maybe I don't need any conditions.
If you're going opposite directions.
Yeah, I'm not sure what opposite directions mean though, because it's.
Right.
I guess the difference between the number of lefts and the number of rights between them has to be 0 on 4.
Ah, yes. Okay. So he said the difference between the number of left. Well, of course, you're assuming that it's only this case where I have these left and right combinations. But more generally, if I had some larger set of basic track pieces and some straights, then if I had built something exotic, I could split and separate as long as I had the same direction in both of these cases. I guess something's bothering me. I can't, because what if I had this? So here and here, the thing has the same direction, right? So, and I can't split there. I'm not sure what center means for some of these curves. Because one of the tracks, when I ran my computer program and it started to find things for me, it started to tell me that I could do things like this. So you can make a shape that looks something like that. I don't know what center means in here. But anyway, it is true that you can find pairs of points where you can rip the thing apart and put in a couple of straights and make something that's longer. Or conversely, if you find a pair of straights that are parallel to each other, then take them out and shorten the curve, and you get something that, I guess I'd like to say that you haven't done anything very exciting to get from one to the other one. So
for this, if you're going around in a certain direction, it seems like the direction vectors need to be kind of like opposite each other. As long as you specify a direction.
I guess that is it. You said something about direction too. So I guess what we need to say is that when you follow the sequence of the curves in the track,
the vectors need to be opposite.
Yeah. So okay, we do need. I have to think about this. I didn't want to get too wrapped up in this, but it is interesting. We have what's called the Jordan curve theorem. Who knows what that theorem is? It's a theorem from topology.
If you have a point inside a closed curve and a point outside the closed curve, then any line crosses the two. Any line between the two crosses the curve.
Yes, that's true. Actually, it's a little more fundamental than that. It says that there is an inside and there is an outside. So the Jordan curve theorem says you have to define what curve is, but it's harder than you'd think. But any simple closed curve does in fact separate the plane into an inside and an outside. And so, I guess we'd have to say is that as you traverse this track, if keep the inside on your right or something like that. And then I have to think about the technicalities.
How do you pick where to insert, like in the one on the right? How do you pick where to insert this way? So like you insert one, right? And you want to insert the other one somewhere?
Yeah.
How do you pick where? Because there's at least two.
Oh yeah, so you're right. So at this point and this point, the tangent lines are parallel, but there's another one point over here where it's parallel, and you're right. So I could insert a straight piece over here, and then I'd move the whole thing down, followed by a straight piece over there.
But
So
you'd still have to insert another straight piece on the, I guess, left lobe, the inside of the left lobe, wouldn't you?
no. So let me see if I can draw these two carefully. So here's the one of them looks like this, and then there's going to be two places here and here where the tangent line is parallel, and then you've got some other goofy stuff happening in like this. But as long as these two pieces are parallel, I do a parallel translation of this one. Maybe it'd be easier to see in the picture if I do a parallel translation of the top part. Just move it up and insert some straights in there. Well, in fact, let's put it this way. This situation occurs often enough that I see two shapes like the circle and the oval, which are not really very different because all they do is there's a couple of parallel straights in them. And if you remove the parallel straights from the one, then you get the other curve. So I guess I'd like to say that they're equivalent. Well, I'll ask you to figure out the right definition of that, but two curves are equivalent if, and then I say something like you can get from one to the other one by removing a pair of parallel straight line segments. Because obviously you can then get not just two shapes, but infinitely many. Going back to the simplest case, I can take the two halves of the circle and separate them further and further by adding more and more straight segments right in there. And now you've got a situation where you have infinitely many different simple closed curves. And so your list of what you're creating is already very long and you haven't gotten to anything interesting yet. So I want to stay with what's interesting as well as, I want to focus on what's interesting. And when I see things if I see like a trivial maneuver that gets me some curves instead of the other ones, then I'll just say, well, take all the things that are trivially connected to each other and think of them as being somehow the same. That's what equivalence classes do for you. All right, so keep that in mind because I'm going to need that to simplify some of my constructions later. Now, let's start to address the issue that I had over there that it seemed like the pieces were coming in kind of crooked, and he was going to break something when he tried to put the pieces together. How do we know when everything works out right? Well, I'll spare you the thinking about this too much, but what you need to think about is when you put these pieces down, you take any given piece, and when you decide where to put it, whether you're trying to connect things up or not, a given piece of train track can be placed on the table, but you have a lot of degrees of freedom for where you're going to put, or how you're going to put the piece of paper down on the table. So if I can appeal to your sort of engineering background for a minute, So I can use a phrase like degrees of freedom, which is nice and vague. How many degrees of freedom do I have for how to put this straight piece on the table?
0.
Oh no, Then maybe if you don't know the term degrees of freedom. Degrees of freedom is like how many separate things can you control? Like when you're controlling the Etch-a-Sketch and you want to get that little dot to move. You've got 2 separate dials, 2 things that you move independent of each other. So that's 2 degrees of freedom. Change the water in your shower. Some showers have a hot knob and a cold knob, so there's 2 degrees of freedom. Some have a temperature knob and a volume knob, that's still 2 degrees of freedom. It's a change of coordinate system on a 2-dimensional manifold. That's in the shower. That's what I get for standing in the shower thinking about topology. So how many degrees of freedom, how many separate things can I control when I put down a straight piece?
4 angle.
Not 4. That's too many.
You have spatial freedom.
I got 3. Why would you describe 3?
Translations and rotation.
Right, so you have 2 degrees of freedom. So in other words, 2 coordinates can tell you where the center of mass of this thing goes. But then once you've got the center of mass right, you can still rotate things around. And that's by a certain angle. So what we need to do is we need to keep track of each of these track pieces that we put in by keeping track of the 3 things. We want to know where we're putting them and which way they're facing. And we'll know that we have things proper when we've got one piece of train track already placed. The next one that we put in has to have the property that, first of all, it goes here, and secondly, it's rotated the right amount. Okay? So in each one of these little train track pieces, I would keep track of the center of the little knob round that sticks out, and then the center of the corresponding hole on the other side. And I want the location of one of these holes to match the location of the other knob. Location has been reduced to a single point. And further, I need to say something about the direction of these things. Now, these train track pieces, the reason they force you to have a direction is because there's a straight edge to the shoulders of each piece of train track, and down here on the butt too, there's a direction, and these 2 directions have to be parallel. So once you get the dots to line up, then the pieces of train track will go perfectly, assuming that those 2 lines are parallel to each other. Actually, they'll be the same line at that point. Okay? So what I need to know is, what I'm going to have to keep track of is something about position and something about orientation. So as I start to construct my tracks, to keep track of, I didn't even realize a little joke in there. To keep track of the pieces, what I should record for each one of them is the position P sub n of the knob on the nth piece. So that's the dot that's at the center of the sticky outy part. And secondly, I'd like to keep track of I guess what I'd like to call the tangent line. That's a vector, or a tangent vector. That's the vector that points in the direction that the train track would go, that the train would go if you stopped your construction right here and the train went speeding off the edge. And where would it go? So that would be the vector. You know what? I won't. I was going to call it V for vector, but I need vectors or something else. I want to use. I'll keep track of the angle that this line makes with the horizontal. So I'll call this. I think I have to call it C sub n. Oops, C. Of the heading of the bearing vector, the tangent vector. Measured to the horizontal, where you draw some coordinate axes to get started. And in fact, I need the coordinate axes to talk about the position here. So if I have an actual train track and I want to start keeping track of all the different pieces, I'll pick one spot to be considered the origin, and I'll let the butt of the first piece of train track determine, I guess I would call it the y-axis, so that the very first edge that you come to on the first piece of train track, it's heading due east. Okay, it's along the positive x-axis. And then you go from there and it twists around. And by the time you get to the end of the train track piece, you could be pointing in a different direction, and so you'll be making an angle now with the horizontal. So a curved train track, if you're curving to the right, I guess you would be going down into the second quadrant, the way I'm setting things up. Okay? By this angle, by that I mean you're measuring the angles counterclockwise. Okay. So I will win this game if I put each piece down so that Pn also becomes the position of the n plus first whole, and this angle Cn is also the angle that, that you get between this vector at the beginning end of the train track piece, that if that matches this C sub n, then the pieces will fit nicely together. And you'll know that you have a closed curve if, when you put down the last piece, the subscripts run cyclically. So in other words, the position of the last knob is also the position of the very first piece's starting spot, which I guess I would consider that to be the origin. So I need the last piece to end at the origin, and I need the last train track piece that I put in. If I'm starting here, and I'm, what did I start with? I said a second ago I was going to go off to the right. So if this is where I'm starting, and then my train track goes around and around and around, I have to end up here with the very last piece facing to the east at the end, and with its little knob coming back to the origin. So I have a criterion for deciding when a sequence of things fits perfectly. Now, I can do, we can use some vectors in here, some linear algebra, to help us work this kind of thing out. Every individual piece of train track has associated to it an angle and a vector. I'll call this angle theta, and I'll call a vector v. And what do I mean by that? So you take your piece of train track, and again, I'll just use a simple curvy one like this. The angle is the change in the direction that the train makes as it comes in on one side and it comes out on the other side. So there's the tangent vector at the left-hand edge of the train track and the tangent vector on the right-hand edge, and these two things will make an angle with each other, and that's theta. And the vector v is the displacement that you get from one end to the next. So this is the vector v, and this is just a little problematic because when I describe it as a vector, it depends on where my coordinate system is. I would like to first measure this vector v in such a way that I'm taking every one of the pieces all by itself and starting it at the origin heading east. And so I'd like to let this thing be the vector v. Okay. Now when you take this piece and you add it to some configuration that you're building on the table, the theta won't change. It'll always be the same fixed change in the angle from where you started to where you're going out. That won't change. But the vector v is going to change, right? Because if I take this piece and later I want to move it, I want to attach it to something that's heading north, well, then the displacement vector from here to here, that's not the same vector anymore as the vector v. How could you describe the relationship between this, I'll call this v prime, and the v that I had over here? It's a rotation. You've applied a rotation to v to get v prime. And how much did you rotate it? Or how would you describe? Well, no, in this case, this is 90 degrees. This v prime in the illustration, this v prime is exactly a 90-degree rotation from this v.
Does it have to be some integer multiple of theta?
Not necessarily, although in my setting it will be because all the thetas are the same for all the pieces. Oh no, maybe I should point out, when you take a straight piece, what's the theta for a straight piece? 0, yeah. Well, maybe you can tell. When I do an eighth of a circle, what's the theta going to be in that case? Yeah, it's a plus or minus pi over 4, because I said I took the entire circle. As you go all the way around around the circle, you go through 8 pieces of the train track. They all make the same displacement in your angle, but collectively they give you a 2 pi change in your orientation. So each one of them is chipping in 1/8 of 2 pi over 4. Okay, so each in my kind of simplified setting, that's all we get is thetas are 0 or plus or minus pi over 4. And multiples of 0, of course, I'm not going to get too much if you restrict me to multiples of 0. But no, the amount of rotation depends on where I left off at the end. In fact, this v prime can be described by saying you take the original vector v and you rotate it. Can I use capital R to designate a rotation? And as a subscript, I'll tell you how much to rotate by. The amount that you rotate by will be exactly this C sub n, where if I've already put down n components, n pieces of track, then they collectively have left me facing at an angle of psi over 2. So I've rotated from, instead of heading east now, what the definition of that psi is that I'm now heading off in that direction, and so you're just rotating the entire picture from east, going through an angle of psi to adjust things. So this vector v it'll be just as long when you twist the pieces around. You haven't changed the distance from the hole to the knob, but you have changed the direction that it sits in the plane. So it's a rotation of that vector. Okay? So here's what's going to happen when I put down n pieces. If I place n pieces with their angles are going to be called theta n, theta I, and the vectors are going to be called v sub I, then I can tell you where I'm going to end up, and I'm going to tell you what my current orientation will be. Actually, the angle is probably easier to figure out. So starting from the very first piece that you put down, it's supposed to start off heading to the east first, and maybe going straight east, or maybe curving to the left or to the right. Okay, and that first piece adjusts you by a certain angle. It changes your bearing by a certain angle, namely, it changes you by angle theta 1. And then you put down another piece, and that'll change your bearing again, and then again and again and again. So how would I get a description of my final bearing after I've put down n pieces that are each changing my angle by this much? Huh? It's the sum of all of those, right? So this is easy. This one is theta 1 plus theta 2 plus dot 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 plus theta n. Now how about the position? Where am I going to end up? The very first piece says you start with the beginning end of the track at the origin, and then go east, and therefore you'll end up at the location v1. But from there, you now launch to go through your second piece. And your second piece is going to translate your position from that location in an amount equal to v2, except it's a rotated version of v2. So in fact, it'll be this. It'll be you take a rotation by psi1 of theta 2. Sorry, v2. And then once you've gotten there, then you'll add on your next piece, and the vector that goes from the hole to the knob will be a rotation of the vector for the third piece, the v3. The amount that you're going to be rotating it by would be the psi2 that you had, which is actually theta 1 plus theta 2. Okay, and just keep the sum going until you get down to adding in whatever the translation is for the last piece, but it will be rotated by this amount that's next to the last rotation. Okay? So I can calculate exactly where I am and what direction I'm facing as I add each of the pieces in, if I can keep track of, you know, what the pieces were that I added in along the way. All right, now I can do this in complete generality. It doesn't matter what the pieces are shaped like. And by the way, I don't even have to have nice circular pieces. If I can have a piece of train track that goes like this. And I don't really care. From my point of view, it just moved you this far, and it did so, and it changed your angle from this angle. Well, in this particular case, it didn't look like it changed my angle at all. But so effectively, this is a straight piece. Okay, so I don't really care about the interior shape. I just get any old shape, and the shapes for me, they're just characterized by these two numbers. And off I go, and I start adding these things up, and I will have a simple closed curve that matches perfectly as long as, well, what do I have to have? When I get back to the end of all of my set of pieces, I have to be back where I started. So what does this have to be at the end? 0, or a multiple of 2 pi. And what does this have to be? You have to come back to the origin. Right? So you have a perfect characterization now of what it takes for the track to close up on itself neatly. Now fortunately, the pieces that I play with are very special, so that, as I said, the thetas are only 0 or pi over 4, and these vectors v, they come in only one of two different shapes. And for the straight pieces, this is either a 1, 0, Or I'll let you do a little trigonometry here. You take 1/8 of a circle and you figure out where that is. It comes out to be the vector square root of 1/2, comma, 1 minus the square root of 1/2. Okay? Which, and that's for the left turn. If you do a right turn, then you change the sign of your second component over there. But in fact, I can swallow both of those up into a single expression. Each one of them is found, that's 1, 0 is a separate case. But then the two curvy pieces, what they do is they take a vector that's this long. You have to trust me on that. Take this vector and then rotate it either forward or back by pi over 8. And that will tell you what the displacement vectors are for this 1/8 of a circle. So hold this so that this edge is vertical, and then figure out the angle that goes from the center of this line segment to the center of that line segment. And the vector is, the angle is pi over 8, and that's the length of the vector that you get to. Okay, so it's easy for me to figure out what to do in here. When I specify these angles, I just say, well, it's either 0, 1 or -1 times pi over 8. Each one of these is some number times pi over 8. And this AI is pi over 4, thank you. And each one of these is +1, -1, or 0. No, yeah, right, 2 pi over 8, pi over 4. And those are the same numbers that I was writing down before for my sequence of things, which, by the way, I think we may have already destroyed this one, because when you look at these angles, every one of these adds pi over 4, and those add a negative pi over 4. And what have we got? Have we got 1, 2, 3, 4, 5, 6, 11, 13, 16 R's. How many L's have we got? 3, 5, 7, 10 L's. If I did the arithmetic right, I don't even get the angles pointing out. So it isn't going to. So that's definitely not going to be a good curve. Okay, this one's a little harder, but not much, because since all of these angles are always multiples of pi over 4, integer multiples of pi over 4, when you start adding them together, those will also be integer multiples of pi over 4. In fact, what you'll be getting for these psi's will just be the running totals of the a's. So I'll call those bi's. So this is a rotation by some number bi times pi over 4. I guess it's b1 times pi over 4. And then this will be a b2 times pi over 4, b3, and so on. Okay, so the b's are the running totals, the partial sums of the a's. Okay, that's great, because I know what the matrix is that represents a rotation by an angle of pi over 4. No, you know what? I really do need pi over 8. How am I getting pi over 4 in here? One moment.
You mentioned over there you have the pi over 8.
Yeah, but that's for something else. Why is this not working out the way I want it to be? Pi over 4 is too easy. 4. Oh, no, wait, it is pi over 4. That's right. Yeah, pi over 4. Right. Okay, pi over 4. Who knows what is the rotation matrix for a 45-degree rotation? And cosine of theta, sine of theta, minus sine of theta, cosine of theta, that one. And sines and cosines both come out to square root of 1/2. So this is what the matrix turns out to be. So when you take a rotation by an angle of b times that number, it will just be the bth power of this matrix. Because to do like a 7 times pi over 4, you just do the pi over 4 rotation 7 times. Okay? If you rotate 8 times, you'll come back where you started. In other words, this is a matrix of order 8. So when you start calculating these things, you'll be taking various powers of that matrix and multiplying them by the different v's that show up. As I said over here, the v's only come in one of two flavors. They're either this vector or one of these two vectors. And so what you end up with here is that everything in sight can be written as it's a collection of some collection of rotations of the vector 1, of the vector, 1 comma 0. Plus, you then add in a bunch of rotations of those other two vectors, the ones that have the square root of 2 kind of thingy in them. I won't write it all out. Okay, and the r's are all going to be powers of those, which you only need to keep track of how many there are where the b's are 0, 1, 2, 3, 4, 5, 6, or 7, mod 8. Because once you get to multiples of 8, they all get swallowed up. Now here you're supposed to be rotating the vectors and then adding them. But all of these matrices lie in a ring, a set of all 2 by 2 matrices, where you can not only multiply matrices together, but you can add matrices. And you have the distributive property in a ring, which means that if you are multiplying a lot of matrices always times the same vector, it's okay to just add those matrices together and then multiply by 1, 0. Likewise over here, you multiply a bunch of matrices, add a bunch of matrices together and then multiply by that other guy. Okay, I will have to summarize because we're getting right to 6 o'clock. Well, I'll tell you now what happens is all of these matrices that I'm collecting, they're going to be powers of this matrix. They've got lots of square roots of 2 in them. And you collect together bunches of them and you add them together. So you might get various components that say things like 4 times the square root of a half or 7 times the square root of a half. So positive integers times square roots of a half. Same thing over here, except you'll have other features that have square roots of a half in them. Square root of a half times the square root of a half is a half, a nice rational number. So everything in sight will represent a vector. That's the position vector. That's the displacement from where we start to where we ended up. It's a vector with 2 components, but both of those components turn out to have entries which are integers and or integers times the square root of 2, or square root of a half. As it turns out, if a and b are integers, and a plus b times the square root of a half is equal to 0, then, more than that, and a is equal to 0. A and b both have to be 0. So in linear algebraic terms, what this says is that the irrational numbers 1 and the square root of 2 are linearly independent over the rationals. Using that fact, when you tell me that you want to have a sequence of track pieces that collectively get you back to where you started, you want this vector to come out to be the 0 vector. It looks like that's giving you 2 equations that make the first component equal to 0 and the second component equal to 0. But actually, you get 4 equations because when you specify that something like this is equal to 0, each of the rational and irrational components turn out to be, they separately have to be equal to 0. So what this tells you now is that the object of coming back where you started translates into exactly 4 equations on all the variables here. What you can vary are the AIs, and from them you get the BIs and so on. In fact, when you write down what's described here, I mean, look at this first equation. This says you need to add together the different angles and see that you get a multiple of 2 pi. Or in other words, you add in these AIs and they need to come out to be equal to 0, mod 8. Well, addition is commutative. You can write down the addition in any order. So instead of saying that a1 plus a2 plus dot 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 has to equal 0, mod 8, it's equivalent to just say, look, tell me how many 1s there are, tell me how many minus 1s, and tell me how many zeros. That's not n variables altogether, just 3 variables. You keep track of how many of each of those things show up. Likewise in here, there aren't really as many variables as there are a's, because I've already pointed out that these rotation matrices can only show up in one of 8 different flavors, because there's the 0 rotation, pi over 4, pi over 2, 3 pi over 4, etc. There's 8 combinations altogether, just 8 matrices, and I can keep track of how many of those each show up. Okay, I will now tell you the bookkeeping device that you can use to decide when a track, a sequence of these things, is for real or not. It's a little algorithm. Getting all the details straight is just kind of following through all the pieces of information that I just did here. So I'm obviously skipping steps, but you get the spirit of it. I will invite you to use the algorithm to test this guy and see if it comes out right. We already know it's wrong. here is a sequence that does work. You first write down the sequence of the track, which is a sequence of zeros, ones, and minuses. Minus 1. So I'm going to do this one by example. Minus, 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 0, 0, minus, minus, 0, 0, minus, 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 plus, minus, minus, plus. Okay, so there's a sample. Then, as we observed down there somewhere, we need the running totals of the b's starting with 0. And these are angles also, but they're multiples of pi over 4. So I only need to keep track of these things modulo 8. So I'm going to make running totals by taking what I've already got and adding in the previous one to get the next b. Add in the running total of the a's to get the b's. So 0 and minus 1 adds up to 7 mod 8. 7 and minus 1 is 6. 6 and minus 1 is 5. 5 and 0 is 5. 5 and 0 is 5. 4, 3, 3, 3, 2, 2, oh, sorry, 2, 1, 2, 1, 0, 1. I messed up some. 3, 3, 3, 2, 1, 2, 2, 1, 0, 1, 0, 7. Is that right?
One of the minuses you skipped.
3 and minus 1 is 2. 2 and minus 1 is 1. 1 and minus 1 is 0. 0 and 1 makes 1. 1 and minus 1 is 0. 0 and minus 1 makes 7.
You have 3 threes? Your last 3 should be 10. That's right. That's right.
I think it's right. And finally, 7 and 1 adds up to 0. So the running total, the next running total would be 0 mod 8, which is the total of all the a's. So the first condition is met. The sum of all the a's is it's a multiple of 2 pi. The sum of all the thetas is a multiple of 2 pi. Okay, now there's a little twist that has to do with the fact that some of these rotations, sometimes I'm rotating just the vector 1, 0, but sometimes I'm rotating this other thing, which is either a straight vector moved up or down by pi over 8. So the little twist that I need to do that it's hard to make it sound reasonable, but it's based on that fact, is that I'm going to reduce the b every time there's a minus sign. When there's a plus sign, I just leave it alone. And I don't actually care what happens when you have the 0 on the top. So these go like this. 7, 6, 5, 4, 3, 2, 1, 0, 0, 7, 7. Okay? Now, remember I said that there was going to be those 4 equations. All you had to keep track of is how many rotations of the different types there are. There's 8 possible rotations, and sometimes they affect the vector 1, 0, and sometimes they affect this other vector. So I need to know how many times I get the vector 1, 0 rotated in each of the 7 possible directions. That's a vector called D. And then another set of, oh sorry, E and F. Where's D? There was no D. So the straight pieces correspond to the zeros. The straight pieces are what gave me the vector 1, 0. And these b's are telling me the angles psi. They're the orientations of the straight pieces. So twice I've got a direction of 5. Twice I've got a direction of 3. And at no other point am I adding a straight piece with those. No other time am I adding a straight piece in any other direction. As far as the curvy pieces, I will similarly just want to scan through this line. I can now ignore the ones with the zeros on the top, because those correspond to straight pieces. But for the curvy pieces, I can see I've got all kinds of different orientations contributing different powers of that rotation matrix R. And the grand total of those is, let's see, I see 3 zeros and 3 sevens and 1 of each of the others. Okay, so in this equation there that involved all these matrices, those numbers, these f's, those are the coefficients that multiply the 8 different rotation matrices. The 8th power of the rotation matrix is the identity matrix. The 4th power is the negative of the identity matrix. So having a fourth power, I mean, a backwards rotation actually contributes, it adds a negative identity to the running total. So in fact, I can sort of collapse this table in half by subtracting the numbers on the right half from the left half. I've got two other sets of numbers here. And I get 0, negative 2, 0, 2. Then 2, 0, 0, negative 2. That's great. Right. Sounds bizarre, right? But remember that there were 4 equations. The 4 equations are the things that link the 4 quantities that are in here. When you get done with all the simplifications, magically the conditions for a perfect match at this point turn out to be that that number has to be the difference between these two. This number is supposed to be the difference between these two. This is supposed to be the difference between those two. And that's supposed to be the difference between, I've lost track, those two. And it works. So I have demonstrated that this actually gives me a curvy track. Moreover, what this does is it gives me an algorithm to list all possible tracks. Here's the way you do it. You need this top line to add up to 0 mod 8. So put down some sequence of the pluses and minuses, any one you want. Don't put in the zeros yet. I'll tell you where the zeros have to go. Then do all the rest of the calculations like I just did. Now you don't actually have to know where the zeros are because they don't affect the numbers in the B column. And likewise the C row, I got that from just looking at the B row and the A row. The E row I don't know how to do yet because I don't know where the zeros are. But the F row, I could get that by just scanning this row. Okay, and then I do some subtractions here, and I got the H row. Those 4 equations, so I said you're going to get exactly 4 equations. Those are exactly enough to tell me precisely what the G row has to be. If I know what the G row has to be, then there's only one way to fill in this E row, except for putting in extra pairs of parallels that sort of undo each other in all of these calculations. So that notion that we had earlier about equivalence, it's exactly rigged up now to give me like a unique solution. Working my way back now, I get the E row, and then I say, well, if you know that the E row has to be 0002, 002, 00, that tells me that you've got to put in 2 straights in such a way that the 2 straights occur to give you 2 extra 5s and 2 extra 3s. And that's the one and only one place to stick them in there. So the theorem is that there's essentially exactly 1 track for each combination of the plus and minus signs that adds up to 0 mod 8. And you can systematically go and get all the tracks. I drew the pictures of a few of them, including hearts, peanuts, the figure 8, which I have to, there's nothing in my algorithm that helps me decide when I'm crossing myself. So the figure 8 has to be allowed, and then you start to get larger hearts. I indicated earlier the little, what's that called, a pince-nez? The little glasses that you put on that squeeze your nose. So there's that shape. There's something that looks like a nose. It comes down like this, and it's got extra wrinkles in that. But you can just you can collect them systematically based on the length of the chain of pluses and minuses. So there's a complete classification for you. Okay? I kept going thinking that the pizza would shut me up. Where's the pizza? Oh, well, why didn't we? I should have had him come in. Yeah, I know. Well, I was like stalling for time thinking, where's the pizza guy? Where's the pizza guy? Is he here? Yep. Oh, well, I'm sorry. Man, if I'd have known he was just waiting out there. All right.